In refraction through a glass slab, first we will find the lateral displacement between the incident ray and the emergent ray. Suppose we take a glass slab having the thickness T. A ray incident on this slab on the surface 1 at an angle of incidence I with the normal. So this is the normal 1 and angle of incidence is I. This ray moves from air to glass. Refractive index of air is 1 and glass is taken mu. So because ray is moving from rarer to denser medium, it deviates towards the normal and the angle of refraction is R. This normal meets at the second surface at point C. Point on the first surface is A and point on second surface is B. This ray again refracted at the second surface because now ray is moving from denser to rarer, so it moves away from the normal and becomes parallel to the incident ray because media outside the glass slab is air. So emergent ray makes angle E, that is the angle of emergence, and it will be the equal to the angle of incidence I. So lateral displacement is the distance between the incident ray and emergent ray which are parallel. The angle between the incident ray and the refracted ray at point A will be I minus R. We drop a perpendicular from B on the incident ray and this meets at the point D. Now we consider triangle ABD, which is right angle triangle. So sine I minus R will be equal to perpendicular oblique hypotenuse, and perpendicular is BD in this triangle and hypotenuse is AB. And BD is the lateral displacement D divided by AB. This is our equation number 1. In triangle ABC, which is also a right angle triangle, cos R will be equal to base oblique hypotenuse, and base is AC by AB. And AC represents the thickness of the glass slab, so it is T by AB. This is the equation number 2. Now using the equation number 2, we can find the value of lateral displacement. So divide equation number 1 by 2, we will have sine I minus R by cos R, and it is equal to D by AB divided by T by AB. This AB and AB get cancelled, so this implies that sine I minus R by cos R will be equal to D by T. Therefore, D will be equal to, this is the lateral displacement, T into sine I minus R by cos R. Next, we will find the shift due to the glass slab in the position of image with respect to the object. Suppose there is a glass slab having the thickness T and refractive index mu. The refractive index outside the glass slab is 1 and there is an object O at a height h from the upper surface of the glass slab. From O, we take a ray which incident normally on the glass slab. So this ray transmitted without any deviation. Another ray we take which incident at the upper surface at the angle of incidence I, and when it enter into the second media, it deviates towards the normal at an angle of refraction R. And when reach at the second surface, again it refracted and it deviated away from the normal and parallel to the incident ray because media outside the glass slab is again air. So angle of emergence is also the equal to the angle of incidence. On backward tracing the first refracted ray, we get a point I1. This is the first image of the object due to the first refraction, and on backtracing the second refracted ray from the second surface, we get the image I2. Suppose distances of these images from the first surface is H1 and H2. So we have to find the distance OI2. This is the shift. So we have to find the shift S equal to OI2. Because alternate interior angles are equal, so angle at O is equal to the angle of incidence I. Similarly, the corresponding angles are equal, so angle of refraction R will be equal to the angle at the I1. Also, the corresponding angle at I2 will also be I equal to the emergent angle I. We also mark the points A, B, C and D. We consider that angle of incidence I and R are very small. In that case, sin I will be approximately equal to 10I and sin R will be approximately equal to 10R. So applying the Snell's law at interface 1, which is air glass interface, and then second interface is the glass air interface. Then refractive index of the first media is 1 into sin I, this is the angle of incidence, will be equal to the refractive index of second media and angle of refraction R. And this implies that approximately it will be 10I equal to mu into 10R. 10 theta equal to perpendicular by base, so we can write it is AB by OA, and it is equal to mu into, and 10R will be equal to AB by I1A. AB and AB get cancelled. This implies that I1A equal to mu into OA. Because we are measuring OA from the interface first in upward direction, so it will be taken positive and distance is h. This implies that I1A will be equal to plus mu h. This is the equation number 1. Similarly, we apply the Snell's law for second interface, which will give mu into sin. Now angle of incidence will be equal to R. Sin R equal to 1 into angle of refraction is I. So this implies that mu into sin R will be equal to sin I, or mu into 10R equal to 10I. So this implies that mu into, and 10R is perpendicular by base, that is CD by CI1, and it will be equal to 10I, this is CD by CI2. CD and CD get cancelled, so we will have mu by CI1 equal to 1 by CI2. This implies that CI2 is equal to CI1 by mu, and this CI1 is CA plus AI1 by mu, and because CA is T and AI1 from the equation number 1 is mu h, so it is T plus mu h by mu. Therefore, we can write CI2 is equal to h plus T by mu. This is our equation number 2. Therefore, shift S equal to, this is I2O, and I2O will be equal to CO minus CI2. CO is the distance CA plus AO minus CI2. CA is T AO is H minus and CI2, which we have calculated in equation number 2, H plus T by mu. And opening, we will have T plus T minus T by mu, or it is equal to T into 1 minus 1 by mu. This is the shift in the position of image.